Welcome to The Explainer. Today, we're diving into a wild collision of two totally different worlds. On one side, you have the bleeding-edge software of artificial intelligence, and on the other, the massive, heavy, physical infrastructure of nuclear energy. We're pulling directly from a highly detailed key logic analysis titled Pathways to 400 Gigawatts of U.S. Nuclear Capacity. It's an absolutely incredible look at how our digital ambitions are literally reshaping our physical world.
But to really get where we're headed, we have to look at the track record. For the past 3 decades, the United States has successfully built exactly 3 new nuclear units. Yep, just 3. That added a mere 3.35 gigawatts of capacity to the grid. This sluggish pace has been totally bogged down by regulatory complexity, economic inefficiencies, lack of policy support, and honestly, a genuine loss of national nuclear know-how.
Now, what's really interesting about this next number is the contrast. We're looking at a new reality. The objective isn't just to build a few more reactors anymore. It's to add a staggering 300 gigawatts of additional U.S. nuclear capacity by 2050. To put that in perspective, we're talking about multiplying our recent building pace by nearly 100-fold over the next few decades. No way around it. That's a massive leap.
Okay, let's dive into this and map out how we get from 3 to 300. We'll be looking at the AI energy crunch, a new nuclear vision, big tech goes nuclear, modeling the reality, and finally, the price of power. Section 1. The AI energy crunch, surging grid demand. For 2 whole decades, U.S. electricity demand has been basically flat. But well, that streak is suddenly breaking. We've officially entered an era where the rapid rise of artificial intelligence is creating an unprecedented physical hunger for electricity, and it's hitting a grid that simply wasn't built to handle it. The key logic projections are absolutely staggering. They model that AI and data center energy demand could multiply by 5 to 10 times over current levels by 2035, and by 2050, over 15 times what it is today. You simply cannot power that kind of exponential growth with our current infrastructure.
Section 2. A new nuclear vision. The government response.
With this impending energy deficit threatening both national security and global tech dominance, Washington is moving fast. The government's response includes specific executive orders from the Trump administration focused heavily on expanding the role of nuclear power. The objectives laid out in the analysis are highly ambitious, accelerating advanced reactor technologies, reforming the Nuclear Regulatory Commission, and reinvigorating the industrial base. The immediate goal is to have 10 new large reactors under construction by 2030, building up to that massive 300-gigawatt total addition by 2050. They're also prioritizing streamlining reactor testing and expanding domestic nuclear fuel production.
Section 3. Big tech goes nuclear. Corporate commitments.
But it's not just Washington making moves here. Massive private capital is backing this push because tech companies desperately need firm, reliable, round-the-clock generation for their data centers. We're already seeing astonishing corporate commitments, at least $20 billion to date. Microsoft actually signed a 20-year power purchase agreement to restart a unit at 3 Mile Island. Amazon is providing $500 million in financing for X-Energy, and Meta has signed major agreements with Vistra, TerraPower, and Oklo for both fuel and new reactors.
And these private investments are building into even larger, coordinated efforts. The administration also brokered a massive $80 billion partnership with Brookfield Asset Management, Cameco, and Westinghouse Electric Company. This is specifically geared to construct the large-scale reactors necessary to meet these surging new energy needs.
Section 4. Modeling the reality predictive analysis.
So, we have grand visions and tens of billions of dollars floating around. But is this 400-gigawatt pathway actually feasible? To figure this out, Keylogic relies on a highly specialized predictive energy model called OL25 NEMS. This is essentially a customized version of the official National Energy Modeling System used by the U.S. Energy Information Administration. It allows the analysts at on location to accurately project these alternative energy futures by factoring in real-world constraints, everything from critical materials to changing macroeconomic activity.
And honestly, the physical reality of this expansion is pretty daunting. To reach these targets, the model shows we'd need to successfully deploy roughly 200 gigawatts of new large reactors, plus another 100 gigawatts of small modular reactors, or SMRs. That means overcoming severe supply chain hurdles and, crucially, reversing that huge loss of structural nuclear know-how we talked about at the very beginning of the explainer.
Section 5.
The price of power. Financial requirements.
So what will it actually take financially to get these physical plants built? Well, the crucial point is this. Initial policy incentives and big tech's billions simply aren't enough on their own. The key logic analysis concludes that massive structural reforms and a sustained, dedicated national commitment are required to establish the necessary workforce and overcome the supply chain challenges of deploying advanced nuclear power at this kind of unprecedented scale.
And here is the bottom line. Beyond current incentives and industry commitments, achieving this 400-gigawatt pathway requires what Key Logic calls a nuclear power premium. They estimate an additional annual average cost of between $69 and $99 billion every single year through 2050 to actually make this a reality. That is an enormous, sustained financial undertaking.
Which leaves us with this final, provocative thought. As the infinite digital ambitions of our AI era collide head-on with the physical limits of our heavy infrastructure, we really have to ask, can we actually afford the massive physical and financial energy required to power our AI future? It's a multi-billion-dollar question that will undoubtedly define the next 3 decades of American development. Thanks for joining me for this explainer, and as always, keep seeking out the data.